the first thing we need to do is put on our safety goggles, because safety is sexy. So the first thing we're gonna do is weigh our marshmallows. So I'm gonna put it on the scale, 32 grams. I'm gonna mark it. $32.
This here is a mechanism that we are going to place the marshmallow in, like so. And in doing this and using this mechanism that is often used to blow leaves off of someone's driveway perhaps, or lawn, or walkway, this mechanism blows the air out at a constant velocity, therefore allowing a small margin of percent error in the velocity of our marshmallows in each trial. We are going to take 4 trials of blowing it across this fine screen of measurements that may or may not have Maya's mom all over the back of them, but that's fine.
How far do you think these marshmallows are going to go when we shoot them through a leaf blower?
10 feet.
10 feet? All right.
I'd say pretty close to that. Maybe like 12 feet, I'd say.
All right. And what makes you say that?
Well, because a leaf blower, like, in a marshmallow, like, it won't really, like, take, like, and the marshmallows look pretty big, so.
I
And
agree.
then the
Way
grass
more.
will probably slow it down, so it's probably.
All right. That's good. Thank you. Thank you so much. In order to get accurate data, we need to make sure we're recording all of our observations onto a nice graph paper.
filling up this bin in order to shoot marshmallows through water.
Six and a half hours later. One eternity later.
So as you can see, we have this blue line in the background that is going at an angle, because what we're gonna do is we're gonna angle the leaf blower down from the top of the water where the blue line starts, and then we're gonna shoot the hopefully marshmallow down along the blue line. So instead of being cut like this, it's gonna be cut like this, but the measurements will be the same. So what we concluded from blowing the marshmallows into water is that the velocity of the air blower was not strong enough to shoot the marshmallow into the water or even perforate the water's surface. Instead, the marshmallow simply bounced off the edge of the surface, and we have no data.
Our marshmallows are ruined. They're quite squishy and wet and weird. And so we're gonna throw them out. And yep, because they...
Unfortunately, because we do not have access to space, we cannot shoot marshmallows through space. However, we can estimate and predict. Because of Newton's first law, an object in motion will stay at motion unless acted upon by an outside force. That in space, since there is no gravity acting as the outside force, the marshmallow will continue indefinitely. In this experiment, instead of measuring the velocity of a marshmallow, we will simply be shooting a marshmallow with this gun through a flame or a heat source to see if we can roast the marshmallow. Is it hot? Wait, show the camera. It's not hot at all.
It's not even roasted. How are we gonna make s'mores?
So now we will be hopefully making a little bigger flame by using an aerosol can full of sunscreen to make a makeshift blowtorch. And when we do such scary things, we always have the hose on standby. Let's go. So Olivia's gonna light the marshmallow on fire. This is not the marshmallow in question, though. The marshmallow in question will be shot through the gun. My heart's beating. Point it
up. Is it roasted?
It's a little warm. It's a little tidbit warm. Just a tidbit warm. So, scientist Sarkeesian, now that we have shot through a small flame and a larger flame, why don't you think our marshmallows got hot?
Well, scientist, human, due to the fact that the fire was not hot enough to actually roast the marshmallow during a short period of time, the marshmallow simply went through the fire, landed on the ground, and was basically unaffected by the whole thing. Kind of like if you lick your finger and stick it through a flame and you don't get hurt. Basically the same thing.
Right, because it was such short exposure and not enough heat. Now, if we had a different chemical that we were lighting on fire instead of air or the compressed air in an aerosol can, we might get better results, even with that short exposure. See, if we had a chemical such as coal, it would burn at 1,977 degrees Celsius, while air only burns, or wood, which is like the match we had, only burns at between 300 and 593 degrees Celsius. So obviously that's a lot higher just with coal, and we might get some better results. Some other things like jet fuel, for example, burns at 1,500 degrees Celsius. But even better, propane burns at 2,800 degrees Celsius, and that might really help us to heat up that marshmallow even in such a short period of time.
So now we're going to be shooting marshmallows through these fireworks that we bought from Kmart. And we're going to be very safe, but it does have a lack of directions, so we're just going to kind of wing it. It says, place on a level surface, light fuse, and get away. So hopefully we'll be all right.
We always have our handy dandy hose with us because it does say to drench after use, so we'll drench it after we use it.
Nothing happened to the marshmallows.
They are perfectly fine, not the slightest bit charred in any way, shape, or form. So in the next experiment, we will be placing the marshmallow on a stick and holding it over the firework the entirety of the explosion. Look at that. Fireworks can, in fact, roast them marshmallows. If you feel the other side, the white side,
Quite warm.
quite warm.
Quite warm.
Not hot, but warm. Nicely melted. And then charred on the one side. If you're into that. Some people like burnt marshmallows. I don't know.
Maybe not for the average s'more, but maybe if you were to roast them more evenly, they would be better for melting chocolate. S'mores.
Yep. If we could get a machine that would rotate them while the firework is going, we would get a nice even distribution. Yes, that is the word I was looking for. Of the heat, and we would get a nicely roasted marshmallow. Why is the water going upwards, Scientist Patrick?
There is more water going down on the other side than going up, and the water going down pulls the water going up.
No way.
As long as the tip of the hose, the one that when it's coming out, as long as that tip is below the water surface, it works. If you lift it above the water surface, it'll stop.
That one went nowhere!
Here's the question, Olivia.
Get into this leaf blower again and taking 4 trials.
Hey, Mr. Martin.